Hello everyone. In this video, we're going to start our discussion of Chapter 11, Gases. I bet you can't take a wild guess what this chapter is going to cover. Gases. So we're going to talk about the behavior of gases depending upon changes in different properties of the gas. And we're going to focus on the behavior of gases and how changing these properties affects the behavior. Air is invisible, but what about its particles? What are its particles actually doing? So we talked a bit in Unit 1 about the nature of gases. Remember, they're just these individual particles basically flying around, not interacting with each other. That's all we really talked about. We talked about the fact that particles are always in motion and that gases have the most freedom of motion with their particles, whereas liquids and solids have a little bit less freedom of motion, well, a lot of bit less freedom of motion, where liquids are able to just kind of slip and slide past each other, their molecules, and solids kind of just wiggle in place. So we know these things, okay, but that's all we really know about them for right now, but they're so critical to life and everything that we do. Every time you breathe in, you're taking in gases to form a chemical reaction to breathe back out. So gases are a significant part of our lives, so let's learn a little bit more about them and what we know about them. So gases behave according to what we call the kinetic molecular theory. So kinetic molecular theory is a convenient way to describe the behavior of gases in most situations. It's not always perfect, but we're going to focus on where it works. And then by the end of this chapter, we'll talk just a little bit about where it doesn't work as well. So kinetic molecular theory at its most basic definition is defined by these four things that you see here on your screen. So first things first, a gas is a collection of particles in constant straight line motion. So basically we're saying we have some collection of particles that we have defined somehow separate from other particles, and they are always constantly traveling in a straight line. So we aren't assuming that they curve at all, that they're doing anything like this. They are always just traveling in a straight line. If they change directions, well then they're just bouncing off at an angle and continuing in a straight line, off like the walls of a container or something like that. So the particles are just traveling in these straight lines, no curves, no nothing. We're just assuming straight lines. Gas particles, for number 2 here, we assume that they do not attract or repel each other, so they do not interact. We talked about this a little bit before. We thought about how gases were different than liquids and solids because their particles weren't interacting. So we're putting it in a little bit more certain terms here. So you may have gas particles that collide with each other or other surfaces like the walls of a container. You'll hear me say that a lot about when we're talking about gases. But you might have them bounce off each other straight off, but they're not going to interact, so they're not going to stick together. They're going to act just like bouncy balls. So sometimes I like to picture myself in a room like my office on campus where I could dump bouncy balls. I could see them bounce off all of the walls. They would just bounce off in these straight lines in all these different directions. And if they crashed into each other, they'd just bounce straight off each other every time. So I kind of like to think about gas particles in a way as these like constantly really fast moving bouncy balls. So there's a lot of space between particles and gases, number 3 here. We talked about this too, where liquids and solids, the particles are all touching. In gases, the particles are not touching. This is the not interacting part of a gas. So for them to not be interacting, they have to have lots of space between particles. And really what kinetic molecular theory says is that it's in comparison to the size of the particle too. So like these particles are so small and there's so much space between them, like especially compared to how small they are. So that's kind of the idea there. Whereas there's kind of some space in between some liquid molecules as they slash around, but it's nothing compared to the huge amount of space in between gas particles all the time. And the last piece of kinetic molecular theory here is going to be number 4. The average motion of the particles is directly proportional to the temperature of the gas. So we talked about this before, that temperature is a measure of the heat energy in a system. So if temperature is measuring the heat energy of the system, the more energy you're putting into those particles, the more they're going to be moving around and moving faster. So the hotter the temperature, the higher the temperature, the faster those gas particles are moving. So they're moving super, super fast all the time. So what does kinetic molecular theory predict? What does it tell us? Why do we care that we have these 4 rules? Well, under those assumptions, using those ideas that we saw on the last slide, we can predict 3 things that gases do that we can observe, okay? So we know that gases are compressible, right? We talked about that. That was something that set them apart from liquids and solids. And it's because of number 3 here on your slide. There is a lot of space between the particles. So if there's a lot of space between your particles, if you just push the particles closer together, you can remove some of that space. And that's what we're doing when we're compressing a gas. We're removing the space between the particles. So liquids and solids can't do this because there isn't much space between their particles. There's no room for error there. There's no room to go and bring it in, okay? So gases are compressible. You can have the same amount of gas in a smaller space or a larger space. Kinetic molecular theory also predicts that gases are able to take the shape and volume of their container. We talked about this before too as a property of a gas. When you put a gas in a container, it fills the entire container, right? So if we go back to kinetic molecular theory, because of number 1 here, that a gas is a collection of particles in constant straight line motion, and because of number 2, the fact that gas particles do not repel or attract each other, they do not interact at all, we can assume that they're able to take the shape and size of their container because they're always moving around with no interaction. They are free to move about the whole container, bouncing off anything they run into without any hesitation, without being stopped or anything like that. So if they're constantly moving around in this straight line motion and they're constantly not interacting with each other, they're able to take that shape and volume of the container as well. So they can take the whole volume of the container because they're not interacting and they're just going in these straight line motions. And the third useful thing that kinetic molecular theory predicts is that gases have low densities compared to their solid and liquid counterparts. So remember that density is kind of an amount of stuff per volume. So we might think about here a number of particles in an amount of space. So what we're saying is that gases have less particles in the same amount of space compared to solids and liquids. So what we're saying is that gas particles are really spread out. This is not news to us in everything that we have been talking about. So because, of course, number 3 again in our kinetic molecular theory states that there's a lot of space between particles. If there's a lot of space between particles, there just therefore is a lesser amount of particles in that space. So if there's a lot of gaps in between your particles, you can't pack them in quite so tightly as you can with a liquid or a solid. And we'll see what happens when you choose to do that in part 3. So this is just a little bit about why kinetic molecular theory is important, and it's because it does describe some of the behaviors that we see in gases. So even though we're kind of not thinking about gas particles, how they might actually behave, because we know that particles are going to interact with each other no matter what, and kinetic molecular theory assumes that they're not going to interact or that they aren't interacting. So it may not be like literally down to the T, but if we kind of make some of these assumptions, we kind of can figure out what the biggest generalizations are about gases and about their behaviors, we can actually predict what gases do and what we see happening when we're observing gases. So it's pretty cool that this theory, if we just think that gases behave according to these 4 steps, it predicts everything a gas does, regardless of the finer details. So it's pretty cool. It's pretty cool. So what does this tell us about the kind of about the characteristics of a gas? Okay. So because gases are bouncing around and bouncing off things, they exert what we call a pressure. So you've probably heard pressure in lots of different ways before, in lots of different areas of your life, you know, like when you have to get up on stage and give a big speech in front of a crowd, you might, I feel the pressure, right? But what do we really mean when we say pressure? Well, pressure is that constant collision between gas particles in themselves and the surface of the walls of the container that is holding them in. So pressure is that constant beating of these gas particles on the outside of the container that they're in, because these gas particles are constantly flying around in these straight line motions. I'm not doing a very good job of making straight lines with my hands. But they're flying around in these straight line motions. They're bouncing off all of these surfaces. So it's that force that the container feels when that particle bounces off the surface. That's what pressure is. And that's why gases exert a pressure, because they're constantly bouncing off the walls of the container. So pressure is more precisely defined as an amount of force over an area. So a force is something that causes an object with mass, our gas particles, to change its velocity. So if it's changing direction, the velocity changes. So the force of that particle smacking the wall of the container, the force of the container pushing back on it, is really what pressure is about. It's that force over the surface area that that particle hits. So pressure is all about the fact that these gas particles are constantly bouncing off the walls of the container, and that's really what causes the pressure in a gas. So another thing that we're going to spend a lot of time talking about here is volume. So volume is that 3D space containing a gas. And remember, we talked about with kinetic molecular theory, because of the number 1 property, the number 2 property, gases are always taking up the total of the volume they're given. So no matter what we're talking about, when we're talking about a volume, we're assuming that the gas is taking up that entire amount of space. I also wanted to remind you one last time that temperature is a measure of the random motion of particles in a gas. So it kind of nails it down just a little bit. We kind of think about temperature as, if I increase temperature, the faster the particles move. If I decrease temperature, the slower the particles move. So I like to think of temperature just as a measure of that random motion, not about like hot or cold or something like that. We're just measuring the amount of motion in the particles. So what I want to say is this, is that the more you increase the temperature, again, the more you're increasing the speed of the particles, and the faster those particles are moving, the more collisions are going to happen between either the particles in the walls of the container or the particles in each other, right? Because if I'm just very slowly moving about and I'm kind of bouncing into the walls, it takes me a while before I get all the way over here to bounce into this wall, before I bounce into this one, before I bounce back again, right? But if I'm moving really fast, I can collide over here, and then I'm over here, and then I'm over there, and then I'm in all the different places in the container, and it doesn't take me so long to get over here. And I'm going, and going, and going, go, right? So the thing is you have to remember that as temperature increases, you have to think about the fact that those particles are colliding more and more, and faster and faster, or faster and faster, and therefore more and more. And that's going to cause different properties to behave different ways in our gases. So the idea here of chapter 11 is to focus on how we can relate the properties of these gases to the behavior of the gases, and how we can describe the behavior of gases through what we call some gas laws. So I'm going to post a couple of videos after this one that are going to be individual videos about each gas law. So tune back in and check out the gas laws.